Alright, section 7.8 is on using kind of different applications of exponent log functions. Of course, we've been using them throughout the whole chapter, but there's a lot of pretty interesting cases, especially in science and finance, where these things are used. We already talked about the Richter scale and the tornado scale, which is called the Fujita scale, from a scientist who came up with that measurement. So there's tons of cases where this is used. We'll only scratch the surface today, but anyway, this will at least give you an idea of where some of these come from. So we want to talk about two basic types of problems: exponential growth, and those graphs look like this, things are growing. Exponential decay looks like that, things are going down. And then something called logistical growth and decay, that recurs to real world scenarios where things stop growing or decaying after a certain time, or they kind of level out. Alright, so here are the basic equations for this. Growth is modeled by this function, decay is modeled by this function. They're almost the same, and this actually looks a lot like the PERT formula from the other section. We're talking about continuously compounded interest. P, or A, is the initial amount. So in a sec we'll talk about radioactive decay. That's like the initial amount of chemical that's in there, the initial amount of atomic substance. E, we already know what that is. That's the number 2.718, and then it just goes on forever. K is like a constant, it's like the rate, and then T stands for time. The only difference between growth and decay is that exponent is negative. And remember, when you have a negative exponent, it's like flipping it and making it positive. So that's going to cause this number to get really big, which means if you take a number, you divide it by something bigger and bigger, the whole thing will get smaller. Okay, and then K is the rate of growth right here, and then right here, when it's negative, K is the rate of decay. So A is the initial value, E is the number we already know, T is time, and K is the rate of growth if it's positive, or the rate of decay if it's negative. Alright, so radioactive substances take a long time to decay. So this will be a decay example. That's why we have the negative KT right there. And half-life refers to how much time needs to pass before half of the substance is gone. So for example, if I have 100 grams of something, after half of its life has finished, I would have 50 grams left. Half of it would have decayed from 100 to 50. 50 is half of 100. So it says the half-life of carbon-14, which is a well-known, I think it's an isotope, if I remember my chemistry correctly. Isotope meaning same number of, I think, protons, I want to say. I could be wrong. Neutrons maybe is the right word. Protons is, I think carbon has, no, maybe it is protons. I'd have to ask somebody who knows chemistry or remembers it better than I do. But anyway, the half-life of carbon-14 means that it decays, half of its amount goes away every 5,730 years. Determine the value of K and the equation of decay. Okay, and this is important right here. When we don't know what the original amount is, and right here we don't know, we use an original amount of 1, because 1 represents 100%. So we start with 100% of whatever amount of carbon we have. So 1 stands for 100%. E is still the same. We don't know what K is. We do know, though, that the time for a half-life is 5,730 years. That's why I'm plugging in that number for T. And then Y is the current amount. Should note that too. A is the original amount, Y is the current amount. How much do we have after 5,730 years? Well, that's a half-life, so that means we have half of it. So that's why I'm putting 0.5. 0.5 represents a half. Okay, we don't really need the 1 there, because 1 is just 1 times anything equals itself. So I'm going to rewrite this like this. 5,730 times K. How do we get the K to come down? We would take the log of both sides. And what log should we take? We should take the natural log, because we're raising e to a power. So what power do I have to raise e to get e raised to that power? I have to raise negative 5730K to that. Okay, equals the natural log of 0.5. And remember, that's the same thing as just swinging that in front. So I just want to clarify that. That's the same thing as doing this. Negative 5730K times the ln of E. What is the ln of E? It equals 1. So that's why we were able to cancel that. Alright, we want to solve for K, so let's divide both sides by negative 5730, and that will give us the K. And you'll probably notice that's going to be a negative number, which makes sense because we're talking about decay right here. And when we're talking about decay, things are supposed to be negative because things are decreasing. So the natural log of 0.5, and we are dividing by negative 5730, and that is equal to this really small number. Now if you want to use that number in the future, here's my recommendation. Press this STO button and store that as alpha and whatever letter you want. I picked alpha k. So what's useful about that is every time I press alpha k from now on, it's going to pull up that number in case I need to use it again. Okay, so that's the value of k. What's the equation of decay? And actually this number is going to be like 0.000121. Okay, let's say. So the equation of decay just basically means this original equation, ae to the negative kt, except with our values actually plugged in right there. So here's the original equation. We plug this in right here. Our equation is going to be y equals the original amount to the negative 0.000, I think it was 121, if I remember correctly. There's our equation. Where do we get that number from? We got it from doing all of that stuff right there. Okay, here's another nice example from science, carbon dating using bones of prehistoric animals, like say dinosaurs or something. So paleontologists, I think that's somebody who analyzes fossil samples. A paleontologist examining the bones of a prehistoric animal estimates they contain 2% as much carbon as they would have contained when original. So again, we're using a decay example because the carbon is leaching out or decaying from that animal. So there's our formula. Okay, how long ago did the animal live? Well, that's asking us to find the amount of time. It's always useful to see what we're actually looking for. We're being asked to find time. And then the second question, we'll get to that in just a sec. But first, let's find time. So here's the thing. The current amount is y, and they contain 2% of the original. They're not giving us the original. So when they don't give us the original, we use 1, because 1 represents 100%. Okay, they don't, the question is, do we know k? And actually, yes, we just found it in the previous problem, so we can use that same k value, which I have stored in the calculator. It was, what was it, 0.00012, I think it was, 121. And in order that we don't get a wrong or an inexact answer, we're not going to use that rounded number. We'll use the one that we actually had. I'll use a capital T so it doesn't get confused with the plus sign. And then y is the current amount. The current amount is 2% of the original. What's 2% of 1? Well, it's just 2%, or 0.02. Okay, so we have to solve that for t. So how do we solve that for t? Well, t is like up here in the exponent. How do we get it down? We get it down by taking the natural log. And remember, this 1 doesn't need to be here. So that's, if that was like a 2 or something, I'd first have to divide by 2, but it's not. Take the natural log of both sides. What's the natural log of of this raised to that power? Is just going to cancel, because remember, we could take that and swing it in front, and then we'd have natural log of e, which is just 1. So we get negative 0.000121 t, and that's equal to this right here. Then to solve for t, we need to divide by this number on both sides. Divide by this number, and remember, I've stored this number in the calculator, and it's important that we did that. We need to find what this equals. The reason it's important is because if we use that number right there, it's going to be pretty inaccurate. It's rounded a lot. We don't want to use the rounded number. We want to use the exact value, which has all those numbers right there. So the natural log of 0.2 divided by, and remember I stored this as alpha k, so we get, oops, something, I think something went wrong there. Negative, what happened there? Oh, you know what, I divided by, yeah, we shouldn't get a negative answer here, because obviously you can't live a negative amount of time ago. Let's see what happened here. So I think we're using, oh, you know what, the problem is we're not using a negative for k. I think that's the problem. We should have a positive number, so I'm just going to multiply that by negative 1. Okay, our k should have been negative to begin with, and it wasn't. So 13,304 years ago is the value. Again, the reason that right here k is not supposed to be, it's supposed to be negative to begin with, and it wasn't. So we get 13,000. Okay, but then let's see if that is, still doesn't seem correct though. Oh, you know what? Here's the problem. I used the natural log of 0.2, and it's supposed to be the natural log of 0.02. So that's my mistake. So let's fix that. It's supposed to be the natural log of 0.02 because that's 2%, and then we're dividing by negative k, because k, in our original problem, we for some reason use that as positive. So 32,000 years ago, that animal lived 32,339 years ago. And then second part here says, and by the way, I just want to show you what would have happened if we used the inaccurate answer. So instead of using k, let's use that rounded answer that we just did. So negative 0.02, instead of using k, we'll use negative 0.000121. So this is the rounded version. And you can see it's fairly close, but it's still pretty far off. You're 9 years off because of the rounding. So that's why we want to store it in our calculator like we did. Okay, the second part, part B, says if prior research points to the animal being 20,000 years old, so they're giving us a time right here. Question is how much carbon-14? How much carbon-14 should be in the animal? Well, that means how much should currently be in the animal. That's asking us to find y in this case. So y is equal to this, and let's fill in our values. We don't know y. How much should be in the animal? Well, we know that the initial amount was 100%. We know that our k value was this number that we found before, and we know that t is 20,000. So basically we just have to plug this number in. There's no variables there, that's just a number. And in just a sec I want to go back a page and talk about why our k was the wrong value, just make sure nobody's confused by that. So let's do this. Let's do second e. There's no equation to solve here, we just have to plug all this stuff in. So negative, and remember I stored that number right there, times 20,000. The k is what we found before. So this is going to be 8.9% basically. It says how much carbon-14 should be in the animal, 8.9% of what we originally had. Just to clarify from the previous page, why did we get a negative k right here? This number right here, let's just verify what that was again. We have ln of 0.5 and we're dividing by negative 5730. And yeah, that's a positive number for k. Okay, the reason that it's turning out to be negative is because when we plug it into this equation, it's getting multiplied by negative 1 right there. So that's just to clarify. I should have stored that as negative k instead of just k. But 8.9% of the original carbon-14 should be present, and we found that as before. We can round that to 9%. Okay, so yeah, this is what we pointed out before. The continuous compounding formula is basically the same as the growth formula for exponential growth. The only difference is obviously P stands for initial amount of money, whereas this little a stands for something like the initial population. In that example we just did, the initial amount of carbon, let's say. E is the same in both. R and K mean the same thing. R for money is the rate, the interest rate, and for population would be the rate of growth. And T stands for time, generally in years. Okay, so that just shows you the connection. So this is talking about the population of the state of Georgia, and this is going to be growth because it's growing. So here's our equation right here. It says determine the value of k. So if we want to know what k equals, that means they have to give us every other variable. So y is the current amount of people, which is this. So I'm just going to fill this in. And we'll do this in millions, so we'll just do 9.36 and we'll know that our answer is going to be millions. A is the initial amount. They told us in 2000 when they started this problem it was 8.18 million. We don't know k. We know that t is the amount of time that's passed from 2000 to 2007, and that's 7 years. So how do we solve this for e? We have to first divide by 8.18. Okay, and so then we're going to get e to the negative 7k, that's this right here, negative 7k, is equal to whatever that number is. Okay, how do we solve that? How do we bring the k down? We need to take the natural log of both sides. We could take any log, but we're taking the natural log because that will allow us to cancel those two. We get negative 7k equals the natural log of this right here. Last step for us to take would be solve for k by dividing by negative 7. And we'll get what k equals, and we're going to store that as a variable this time. We'll store that as alpha k. So let's plug this stuff in here. So we'll clear this. The natural log of 9.36 divided by 8.18 and then we're going to divide that by -7. This should be a positive number because it's our rate of growth. And so why are we not getting a positive number here? -0.01. Oh, you know what? Because I used the wrong equation, that's why. This is supposed to be, up here I had positive KT, and for some reason I put a negative there. That's not supposed to be negative. It's just supposed to be 7K. So all places here where you see a negative should not be there. Sorry about that. So get rid of this, get rid of that negative right there. So let's just redo that, except this time without having a negative there, because we want it to be a positive number. So it's growing at 1.9%. So let's store that as alpha k again. And by the way, that's going to override our other k. So if you want to store multiple values, you have to pick a different letter for that, but we don't care about the carbon problem at this point. Okay, so 1.9% growth, so that is our k value. That answers the first question. Second question, when will the population reach 12 million? So with all of these problems, we want to figure out what part of this equation right here are they asking us to solve for. When will the population reach 12 million? That's a question about the current amount. When will the current amount be 12? And current amount refers to the y value. So we want y to equal 12. Okay, our initial was 8.18. We found k. K was 0.019. I'm just rounding it there. We'll use the exact answer. We don't know t, and here's a clue. They're telling us when, and when is a question about time. So we want to solve for t. Okay, so how do we solve this? We will divide both sides by 8.18. And we're going to get e to the 0.019t is equal to this number. Okay, how do we resolve that? How do we get the t to come down? We'll take the natural log of both sides. Okay, and that means the natural log of, sorry, that thing should go right there, 12 over 8.18. Last step is to divide by that k number that we found before. And then we're going to take this whole thing and plug it in, and that will give us our t value, amount of time needed before we reach 12 million. Okay, so let's do that. So the natural log of 12 divided by the initial population, and then we divide by that number we stored as alpha k. And 19.9 years is the amount of time. So in about 2019, 2020, population will reach that value. Last question, Michigan's population was 9.9 million, and it will be modeled by that. Determine when Georgia will surpass Michigan. So here's the easiest way to do this. Graph both of these in a graphing calculator and see where they intersect. So let's clear all this stuff out for a sec, and here's how we do this. So let's start with Michigan's. Michigan's is 9.9, and that's going to be second e raised to the 0.0028, and I'm going to use x instead of t. It doesn't really matter. Let's just see what that graph looks like, and actually we can't see it, so let's do zoom. Let's make sure we're in the right standard. Still not a great picture. Let's do zoom fit. That's still not a very good picture. So you want to get a graph that kind of looks like an exponential. Did I put this in correctly? Let's see here. 9.9 e to the 0.0028x. That seems right. Sometimes you have to play around with this graph a little bit to get a better picture. Yeah, so now I'm zooming out right now. That's giving us a better looking curve right there. By the way, we only care about the stuff that's to the right of x equals 0, so I'm going to go to window and put my window at like -1 right here. The reason is x stands for time, and it doesn't make sense to have time being negative. Same thing, population, we only care about like 0 and above because we didn't have a population of negative, so I'm just going to put -1 just so we can see where the graph starts. And let's go up to 40 million. We'll go by 5s. This might give us a better picture. X max will say 100 years. Okay, so this, let's see if we can change that a little. Let's do by 10s right here. So that gives us a decent, I mean, it obviously shows it's going up. We might want to expand this a little bit more. So let's make that 200 years, and let's make the y max equal to 100 this time. Sometimes you have to kind of experiment a little with these windows. Okay, so it is growing at a slow rate. Now let's put in the Georgia equation. Georgia is 8.18 million times second E, and we are raising this to that number we stored as k before, so alpha k times x. Let's graph that, and you can see at some point Georgia starts to rise a lot higher, and we want to know exactly where, so we go to second calc, and then we want to find the intersection of these two. So right now my arrow's on the blue line, I press enter. It's on the red line, I press enter. I'm going to go pretty close to that right there. And it looks like x equals 11.6. So after 11.6 years, so sometime in 2012, 11 years after 2000, that's when Georgia's population will surpass Michigan's, right around the year 2012, which was obviously in the past, so we'd have to double check that. But off the top of my head, I'm not sure what those populations are. Okay. Here's the last thing I want to mention, something called logistical growth and decay. So here's the problem. If you look at that graph that we just did, okay, look how steep that red curve is. You can see it's going way, way up there, and the problem is in real life that's probably not going to happen. Okay, this is what the graph looks like right here. According to that graph, it's telling us that Georgia's population will shoot up to 1 billion by the year 2130, and that doesn't make sense. That's what we mean by logistical growth. What makes sense in actual real life? Okay, and what they're telling us here is populations don't grow to infinity. Obviously, there's wars, diseases, famines, things happen that result in the population being restricted somehow. Okay, exponential growth is not restricted, and so we need to come up with a new equation that has some kind of limit built into it, because models need to account for the fact that limitations occur. So they have something called the logistical growth function. Here's what it looks like. Okay, this basically means you have some value. C is usually the we'll see what it looks like in just a sec. Most of these values are the same. T is still time, A is still the initial amount, E is the same, and then B is a constant that's going to give you kind of that limitation that we talked about. Okay, so here's what we have right here. So 2.066, that number on the top, that's the initial population of Phoenix, Arizona, in millions. Okay, and they want to know essentially what a couple of things that were being asked. First of all, graph this function, so we're going to put that into the calculator. Okay, so let's put in 2.066 right here. We'll clear these other examples out right here. So 2.066 is the initial population, and we're going to divide by this whole thing. 1 plus 1.66, and then E is being raised to the negative 0.048, and I'll use X again instead of T. Okay, we want to graph that from 0 to 500, so I'm going to go to Window, I'll put 0 here, and that's going to give us the population for the next 500 years. And usually your X scale, you should take this max and divide it by 10, because that way we won't get 500 little dots. So 500. Let's see what the picture looks like. That's not a very good picture. The Y is too big. So let's put that at, let's say, 8 instead. Population. And we'll make these go by Y scale by 1. Okay, so that's a bit, and you can see that's kind of what it looks like. The population grows and then it kind of levels off. It's still going to be growing a little bit, but it's never going to quite go past a certain point. It's like, that's called an asymptote. T, by the way, in this equation stands for number of years after 1980. So we graph that. Horizontal asymptote means where does the graph go as t goes to infinity, or as x goes to infinity. And if you want to answer that, basically we're being asked, what is this this line right here, that blue line, where is it leveling off to? And here's the easiest way to do this. Take t and make it kind of go out to infinity and see what happens. And you'll see the pattern pretty quick. So 1 plus, what's going to happen to this thing as t gets enormously large? Let's do a sidebar over here. So 1.66, remember, raising to a negative exponent means flipping it and making it positive. And we're only flipping the e because that's the only thing that the negative exponent is attached to. Okay, what happens as this gets huge? Okay, well, as that thing becomes huge, this whole number becomes enormously large. And 1.66 divided by a huge number, just think about if you had 1.66 of something and you divided it among an infinite number of people, everybody would get practically nothing. So this whole number right here is going to go towards 0. So then what does this become? This becomes 2.066 over 1 plus something that's basically 0. So that's the same thing as 2.066 over 1, and that obviously equals 2.066. So here's how to check that using the graph. The asymptote should be y equals this number. That should be our asymptote. Here's how we can check that. Let's just graph that line on the graph and verify that it kind of levels out towards that. So y equals 2.066. And you can see there, I mean, clearly they're kind of matching. Let me just zoom in so you can see that a little bit better. You can see they almost look like they're right on top of each other, and the blue gets very close to it without ever touching it. C, will the population increase indefinitely? No. And what's their max population going to be? It's going to be that number right there, 2.066. According to the function, when will the population reach that number? Well, here's how we can do that. Let's graph 1.8 and then find the intersection. So 1.8 is right here. We will graph that. And actually want to zoom out right here so we can see that picture better. So you can see the intersection is like right there, and let's do second calc intersect to see when that happens. So I'm on the first curve, that's the blue line. I'm on the second curve, that's the red line. Let's get close to it and guess. I'm pressing enter for each of these. So x equals 50. So after 50 years after 1980, because that's when we started, so about the year 2030, population would be 1.8. Okay, that's what the model says. So that is just a very brief intro to how you can use logarithms and exponentials in a lot of real-world situations: population growth, radioactive decay, paleontology, finance. There's a whole bunch of cases. We just scratched the surface, but hopefully it gives you a picture at least.